Okay, so linearizations are a thing to approximate functions over short intervals. A lot of early calculus had to do with the fact that most real-world things are curved. And people didn't really like curves because algebra is not curved. Algebra, everything is straight. So if we wanted to figure out the slope from here to here, they were pretty happy with that because they would just sort of act like that's a line and do the slope. But if we wanted to do the slope with only one point, that was like the whole development of derivatives and all that. Part of this package was, at some points, they would take something that was curved and kind of tear it up into pieces like I just did. If I stay over a short piece of this basically is pretty close to a straight line. Is it a perfect match? No, but if you're in the 1600s, close might be good enough for you. You know, they weren't sending people to the moon quite yet. So like here's another short piece that's pretty straight. You know, here's another piece that's pretty dead on straight. You know, they were portioning this up to stay over short intervals to figure out like approximate things. And once I'm over there, I'll talk about that when we get over there. You have the benefit of calculators. In the pre-calculator days, there were things that were quite a chore for them. So here's the rule on this. If we have some sort of a function, y equals f of x, whatever it may be, if that's differentiable, meaning you can do the derivative at a certain point that I just called a, so I had something to call it. Quick recap, there were three places, reminder, not recap, but there were three things that we, on a graph, could not do the derivative. Do you remember those things?
Vertical.
If it went vertical, this whole idea would go out the window because it's not differentiable.
Corners.
Corners make not ability to do derivatives anymore. And then discontinuities. If we had holes in our graph, then this goes out the window. But as long as we can do the derivative, we're able to apply this thing. So the linearization is going to be like a sort of shortcut formula to replace this formula. We're going to need to plug the number they give us into the original function. We'll need to plug the original number they gave us into the derivative. And then in parentheses, we're going to have x minus the number that they give us. We can connect this to a thing that you already know. What's the derivative, the synonym for? Slope. What is, like, this stuff usually a synonym for? Y. Do you remember something that looks kind of like that? That's true. A thing that looks even more like that connects to y equals
so y minus y1 equals m times x minus x1.
Which is an equation for writing a line. So that's what we're trying to do, is write equations for lines. So we've done this a lot from Algebra 1 to the modern day. The derivative is the slope, the x is an x, the a is an x coordinate that they're going to give you. If you look through the couple examples on the board, the number I'm giving you each time, it's x equals some number, or x equals some number. You're always going to be given an x coordinate. This, if we plug in, if we take the x coordinate and plug it in, this is like our y1. This is like a replacement for the y. So if we do a little algebra shuffling, it's the same equation you've been familiar with other days, just dressed up in a new name and a new setting. Question about concept. So here's how you do this. The first thing you're going to want to do is do the derivative. We're in the derivative chapter, and I've said this a few of these lessons in this chapter. When in doubt, just do the derivative and get something accomplished. So if I ask you to do the linearization of this thing, I'd rewrite this as 1 plus x to the half. Then I'll do the derivative. Derivative of that would be
Half plus half x.
half
1 plus x.
1 plus x
Negative half.
with a negative half. For plug-in purposes, you might be better to re-express this with like the radical symbols back in, like a 1, a 2. This 1 plus x had a negative power, so it's on the bottom. and it's still half powered, so it's still rooted. That's your beginner step. Just do the derivative so we have a formula to look at. Then we're going to take this number and plug it into the original. 0 plugged into that makes 1. 0 plugged into this makes a half. So then the linearization is going to be what we got from plugging into the original, which is the 1, plus the slope, which is what we got from plugging into the derivative. And that wants to distribute x minus the 0 itself that we put in a second
Where'd you get the first one from?
ago.
Oh, okay.
So plugging into the original gave us a y-coordinate. Plugging into the derivative gave us a slope. Your biggest threat on a quiz is that you forget which number goes in which slot,
Okay.
but then connect back the stuff you've been doing since Algebra 1. The slope always goes with the x. So the derivative we're familiar with means slope. So if derivative means slope, the slope goes with x. Make sure you put the derivative number with the x minus stuff. And then clean it up. Best, most clean answer here would be
1 plus half.
1 plus half x. To you, that's not a big deal. Because we own a calculator. But what this would be useful for is, as long as we stay close to 0, like 0.01, back in the olden times, they would not have been real enthusiastic about doing the root of 1.01. You don't care. You just grab your calculator and punch in root of 1.01. If your calculator's handy, just punch with me and you'll see the results instead of having to listen because your eyes might be better off. So if x was like a 0.01, the root of 1.01, I'm getting a 1.00498. If I instead put the 0.01 there, 1 plus a half times 0.01, it says 1.005. You wouldn't mind doing a 0.01 into this by hand without a calculator. You'd mind a little bit because you got spoiled by calculators, but multiplying by 0.01 and dealing with this, well, that's not bad. But like doing the root of 1.01 would be a real chore. But the payoff here is root of 1.01 was 1.00498. The true answer is 1.005. So if you don't mind being off by 0.0000 like 12, you'd much rather use this formula. Especially if at the same time sitting down, maybe you needed to do the root of 1.001 as part of your chore that day. The root of 1.001 is an even longer thing. But if you do 1 plus a half times 0.001, it's almost the same identical thing. So if you had to do a bunch of roots that were a little bit above 1, you'd probably be willing to do the payoff of doing a little bit of calculus to replace this with that and then do roots of 1.0 stuff and not have to be bothered with it. You've never done a square root the long way. Some of our algebra books have a technique to do that. No one uses it anymore, so I don't even do it. It has something to do with dividing and averaging until it like works out. And I won't even do this on the video because I don't even remember the strategy. We'll cut the video and then I'll see if I can remember the strategy and show you how people used to do roots, but it's messy. Question about concept. So if I do an instant replay, but now I want my x's to be around 3, would that change at all the derivatives that we did? Would I be able to reuse these or do I need to start fresh? I just reuse those. It's the same formula, it's the same derivatives. I just need to do a different plugin. So instead of putting in 0, I'm putting in 3. So 3 into the original. 2. 3 into this derivative,
1/4.
1/4. So then when I write the linearization, it's always going to be this plus that, parentheses, x minus something. What number goes here? That's the 3. Who goes here? 1/4. And then who goes here? Is a 2. If we distribute and try to clean up, we're going to get a 4th x. And then what will be the other missing piece? 1 1/4 is fine. 5/4, 1.25, whatever you like. Question about that? If I give you, I don't know why I wrote the parentheses there. If I give you tan x, and I'll do an x equals 0 again, how are we going to start off? Derivative of tan, secant squared, then plug in 1 or both? Both. Tan of 0. 0. Secant is based on cosine. Cosine of 0 is 1, but secant needs to get flipped and squared. Final result, still 1. So we got, this time we hit it pretty lucky. We got 2 zeros and a 1 to insert. So is this a 0 or a 1? That is one of the zeros. That's the 1. So that's the other 0. Cleanup time is x. Tan looks like this. Y equals x. Splits those quadrants in half. And I didn't draw like the most precise drawing of tan to begin with, but the idea is, as long as you're close to the origin, these two should have been a pretty good mimic for each other. Enough that if you were in the Wayback Days and you didn't have calculators and you wanted the tan of .005, you could probably just use .005 and be okay without having to try to do some crazy thing or look it up in a table or do something ridiculous. Cosine. Again, start as everything in this chapter by doing the derivative. Derivative of cosine is negative sign. If you're uncomfortable with pi/2s, make them degrees. If you're good with pi/2s, leave it pi/2, but add in degrees, that's 90. Cosine of 90 is 0. Sine of 90 is 1, but in this case it's actually negative 1. And just stick the right number in the right slot. That's the 0. It's the negative 1.
X minus 0. Oh, wait. Not,
You want?
90.
We could think 90, we can't use 90.
however.
We're stuck with pi/2. So we get a negative x plus pi/2. And on we go. Most of that time you're probably waiting for the hard one to drop. There isn't really a hard one. The only thing that could make this hard is if they decide to make a formula that's harder to do the derivative. I probably came in on the hardest one because it took a little more work to do that derivative than these. Now in the homework, might they pop you like a product rule or something? I mean, they might. I don't know. But the only thing that can make this hard is how hard is the derivative to do. But once you have the derivative obtained, plug into original and derivative, and then you just swap them. Here's a shortcut that helps on at least one of the questions in the homework. Relates back to the one we started with, where we had 1 plus x go into the half, and the answer was 1 plus half x. I mean, historical people were always on the lookout for patterns and trends, just to save work, as are the modern day people, I suppose. If you have 1 plus x in parentheses to a power, the answer will always be 1 plus kx. That power can just slide before the x, if the x is close to 0. That didn't work over here when x was 3. There's no way to shortcut this, really. Okay? But if x is 0, 1 plus x to the half became 1 plus fx. So if I said 1 plus x to the 10th, what's a pretty good guesstimate of that? 1 plus 10x. You know, so in olden days, instead of trying to take 1.1 out to the 10th power, they might just do 1 plus 10 times 0.1 as their like guesstimate.
Would it be 1 plus the absolute value of kx?
No, if the original had a negative power, it would live on.
How come it didn't?
The original thing was to the positive half power.
Oh, okay, I was looking at the
Yeah, not at the derivative. The original. And likewise, if it's 1 minus x to a power, that's just 1 minus the power times x. That was like a decent little shortcut that they figured out. Obviously, maybe not obviously, but once I say it, obviously, the closer you are to the number, the better this works. So on this one, if we're trying to do this for x equals 0, and you're using 0.5, that might not be the greatest thing. 0.1 would be better, 0.01 would be better, 0.00001, that's even better. The closer you are to the number, the better this trick goes. That's what we got. Homework off of this, I think, is at 1 to 19, if memory serves. Yep, 185 from 1 to 19 is true. Question on that? If you wondered how they used to do square root